will not be reaching as targeted. And therefore, I think this iConnect event is very important, and especially cross-disciplinary carbon capture, carbon capture and valorization. These are the three basic themes, or you can say three basic terms, which are frequently used in climate change actions. Because carbon dioxide generation actually cannot be eliminated totally, because energy production is invariably associated with carbon dioxide production. And therefore, if you don't want to release this carbon dioxide into the atmosphere, we have to capture it. Then again, capturing carbon dioxide is not enough, because you have to, if possible, you have to valorize it. You have to make a value-added product or some chemical from this, or else you have to sequester it permanently, so that other in inorganic form, so that it is not released back to the atmosphere. So carbon capture cannot be a temporary phenomenon. It has to be either converted, carbon dioxide has to be converted to some value-added product, or carbon has to be completely sequestered in inorganic form. And there are many technologies. The major issue which we have to face is that whatever technology or science we are propagating, it has to be really carbon neutral. Means we should not, by capturing carbon, we should not generate more carbon dioxide in some other form or at some other place. And therefore, I think a lot of brainstorming is required, not only brainstorming and brainstorming such events, series of such events, which are planned by Ministry of Science and Technology and CSIR and institutions across the CSIR, are very much essential to arrive at the plan. What I personally think is that there has to be a concrete plan how we are going to achieve this by 2070, covering all aspects of carbon capture, valorization, and sequestration. This is a truly interdisciplinary truly interdisciplinary task, because we need expertise and inputs from all branches of science and technology, because it's a global thing. It's encompassing all the branches of science and technology. And therefore, I'm sure that today's speakers will speak on different aspects of this cross-disciplinary carbon capture, valorization, sequestration. And this may not be the end of such series. Finally, we have to arrive at the implementable plan, and this will be a first step towards this. And I hope this interaction continues. This is a 2 hours program, but nevertheless, this is the beginning from NERI side. This continues for long time, unless we are at the target. So therefore, with this these few words on my concepts, I stop here. I welcome you all again, and I am sure that it will be a very fruitful interaction, and we will come out with some conclusive things at the end of these 2 hours, which will take us to the continuity of such programs. Thank you very much. Welcome all. Thank you.
Thank you, sir. Thank you very much for your introduction and opening remarks. So today, 2 hour session, we are having 4 speakers. The Dr. Sukumar Devata, our former director, CSIR NERI, and Sri N.N. Radia, the Chief Operating Officer and President, the GHCL Soda Ash Wing. And we are having Professor Sebastian Peter from JNCAR, ASR, Bangalore, and Dr. Sadhana Rayalu, Chief Scientist and Head Materials Division, CSIR NERI. So after 20 minutes of each speaker talk, there will be a panel discussion, that is questions asked by the people sitting in the auditorium will be put to the concerned speakers. So I request all the speakers to be there up to 12 o'clock, so that the audience can interact with you. So now I request Dr. Sukumar Devata, former director CSIR NERI, who is going to speak on carbon capture, valorization, opportunities and challenges. So before speech, So I request to read out a short biodata of Dr. Sukumar Devata. So I request Anshika Yadav to read out the biodata of.
Make it really short. Make it really short.
Thank you, sir. Good morning, one and all present. It's a great pleasure for me to introduce our first speaker, who is going to address opportunities and challenges in the field of carbon capture and valorization. He is the distinguished alumni of AC College of Technology and Salford University, UK. He began his career as scientific researcher at CSR NCL and later served as the director of CSR NERI. He has and continues to serve in many prestigious national and international committees, UNEP, IPCC, CPCB, World Bank, to name a few. He has been listed in Stanford University top 2% world most cited scientist in environmental science for last 3 years. A prominent contributor in the field of energy, environment, and green technologies. Please welcome Dr. Sukumar Devota.
Yeah, that's very good. So can you see my presentation?
Yes,
Yes,
sir.
sir.
Okay, I'm going to make, okay. So thanks for the invitation, Dr. Vaidya and Sadhana Railu and Kripadam. And I'm very happy to be speaking on carbon capture because this is one of my favorite topics and I'm involved for a long time. I continue to be involved through DST and other EU programs. What I thought was, time being short, I will just speak about the importance of carbon capture, utilization, and storage. The presentation is based on my personal experience and as a chairman of a DST, carbon capture program about a decade ago, and then member of DST EU review committees and peer reviewed literature. So I've made all these things into my presentation, and I will be just speaking on the potential and options for CCU, current status of CCU, challenges for CCU, and conclusions. I'm not touching too much on storage, although I'll be mentioning a few important aspects. If you look at carbon dioxide, emission is far more than its utility. So if you look at this, you can see that most of the emissions are from power. Bulk of it is from power, cement, iron and steel, and chemicals and petrochemicals, aluminum. But what is demand is only a fraction. The demand is 230 million tons per annum, while the emission is of the order of gigatons. And what we need, again, to achieve even the target of small 1.5 degrees Celsius target for 2050 or so, what is required for capture and sequestration is close to 750 gigatons. I know while our consumption is in billion tons, so we are away from the potential need target and what we have achieved so far. And most important message in this is CCV is not considered to be an alternative to CCS for large scale emission reduction. It's only a complementary. What CCV can achieve is only a small fraction of what we need to do. That's the message I wanted to give out of this slide. And why CCS? It's of the global view and my strong view that coal will dominate still in the power generation. See, this is coal used versus the reserve. Globally, we have a huge reserve and we have so far produced only a very small fraction of it. If you go to other things, we have consumed quite a lot of the reserve, but coal has a huge reserve. And if you go to the global power production, you will find that coal continues to be the dominant source for power, thermal power stations. And it is projected even by 2030, 2050 that it will continue to dominate. And therefore, the carbon dioxide emission will be a major issue, and you cannot avoid it. And for net zero commitment by 2070, I'm sorry, it is 2060, it is that we need to work on many aspects, including renewable energy, and CCU is an option for decarbonization. And if you look at it, the largest single point source is thermal power station. And as I said, coal is the main thermal power station because coal is the main dominant source of power. And you can also look at metallurgical, cement, oil, and most of the demonstrations are taking place in thermal power stations, but there are some demonstration in cement and oil gas. And but we need to look at, when you do thermal power stations, you need to look at the pre-cleaning costs, because we have to do soot cleaning, DSOX, DNOx. Otherwise, whatever you do has to withstand, or you should be able to handle with some SOx, with some NOx. And we do not have much of reliable cost for the entire CCUS production in India. How CCUS? This is a standard. This is the time when I was involved in IPCC in 2000 and 2005 and all that. This is the first slide which IPCC put out for CCUS, and we have many options available for CCUS. But post-combustion is the most popular, although pre-combustion is possible, or oxy-firing, and you will be ultimately the cost involved is the regeneration of separated CO2 and then transporting it for certain storage. And you will find that most of the activities in India are for enhanced oil storage, EGR, and enhanced coal bed methane recovery. But we have a lot of R&D activities, but still I feel that R&D activities do not address the realistic thermal power station exhaust. And what we do not have much is pre-combustion capture and air separation unit for pre-combustion capture. Most of the activities are for post-combustion capture, and that too in R&D activities. And we still have to do something about direct air capture, but we have some activity on algal process, which is encouraging. I'll talk about it a little later. There is no CCS has the greatest potential towards net zero. I keep saying, I know CCS, particularly storage, and we have many possibilities for this, for separation, storage, direct use, and conversion into products, and conversion into other products. But conversion to other products, particularly fuel, is very attractive because it leads to circular economy. You produce carbon dioxide from fuel, then you reproduce fuel. That means you can use it, reuse it, and it leads to the circular economy. Biological process is very interesting because that can also lead to, if you can increase the lipid content in the biological product, then you get into the circular economy, because the biological products can be, like biochar, can be converted into a fuel source. Direct air capture is the most difficult one because its concentration, we are talking about 400 to 410 parts per million. When the partial pressure goes down, it's more difficult to capture CO2, but still people are looking at it as a major option. One major reason, one important reason is it can be done at any location, immaterial of the large single point source, because atmosphere. You can do it, and then you can do it close to its utility. Suppose you have a plant for utilization, you can capture it and use it then and there. So two things are important. The most important thing is transportation cost, which is a major part of the CCS US, is removed, and you capture it at the point and then use it very close to it. But still the challenge is it's a low concentration and therefore the cost is likely to be high. But there are demo plants now, and this is an actual demo plant of direct capture. My opinion about biocapture is a very positive, because this is where I find that you can capture it like raceway ponds and then convert it into algae, and then if you increase the lipid content, you produce fuel, and otherwise you can also have, there are many options for biomass utilization. I have visited quite a few plants in India. One of the largest was in NTPC, and they were manufacturing, where they were producing the biomass and selling it for whatever use the user can think of. And the lot of work is going on all around India. This is considered to be one of the negative emission technologies. That means, I keep saying, whenever you do look at an option, the most important thing is whether it is at least carbon negative or carbon neutral. If it is not carbon negative, then we are not doing any favor to carbon capture towards net zero. Exit to mineral carbonization is another, and this is now currently practiced in India. There is a plant in South India where they are capturing CO2 using traditional mixed amine solution and then converting it into soda ash. There are many opportunities for mineral carbonation, but the most important thing now is in what is being practiced in India is converting it into soda ash, and it is in the fertilizer industry, and it can be used. But there are many opportunities for mineral carbonation using even waste, industrial waste like red mud. Yeah, and we had worked on a red mud from aluminum industry. It has a great potential. There are many such opportunities, including cement, where people are talking about developing cement, where when it cures, it absorbs CO2. These are all exciting possibilities, and they are also supposed to be net emission technologies. CCU option for chemicals and fuels, I'm not going to talk about it because I see a couple of experts going to talk about it. But then the most important thing is already technologies are known for methanol, methane, formic acid. All these things are known, and these are very exciting. And in polycarbonates and polyols, people have to work on this, but remember, we have to see whether it is a net carbon emission technology. There are challenges for thermal power plant in India because they have certain limitation with respect to cleaning, and using a coal which is with high hash and low calorific value. Therefore, you need more cost for cleaning, and this will add to the cost of the carbon capture in India. Talking about cost, I find this is in a cost estimate made by Global CCS Institute. You can see that cost is varying from 250 US dollar per ton to something like $50 per ton. But if the partial pressure of CO2 increases, cost is coming down. So when it is when you're talking about direct air capture, that means total cost can be very high. But if you are reducing the transport cost, it can come somewhere in between. So it all depends on where you want to look at it. That's why people target 10% CO2 in the flue gas as the best option. It's a beautiful report by Global CCS Institute. In 2021, there are so many projects available, and these are all over the world. And you can see that this is a capacity and how it is happening in various areas: direct air capture, cement, iron and steel, power generation from coal, hydrogen production. The options are quite a variety, and they are increasing. But what is interesting is they are becoming bigger and bigger. Now, of late, all the projects are very big, huge, gigatons. And I reviewed a project on gigaton project from Norway. So they are talking in terms of gigatons of capture and storage. So the projects are becoming huge, and this kind of gigaton projects are important to keep the global warming limit to 2 degrees Celsius. The problem with the storage in India is Indian society is generally opposed to any subterranean activities, because there are a lot of perception about environmental impacts and apprehensions about environmental impacts of subterranean activities. And NERI should look at it as what are the environmental and social impacts of carbon storage? Because until this is, you remove the euphoria and the anti-feeling of subterranean activities, we are not going to achieve large carbon emission reduction. And we will be working on, even as a policy, we are not looking at carbon capture storage. We are only looking at utility. That's a political message which the government wants to give. But what it can contribute, valorization can contribute, is a small fraction. And therefore, we need to know, we need to identify how we are at net zero with yeah. So ultimately, I'm summing up, the capture is important. There are options from industries, thermal power plants, including direct capture. You can convert it into utilization by transformation, chemical transformation for methanol, dimethyl ether, alkanes and alkynes. And it's already being used in many places like urea, but these are all traditional uses. And you can convert it into carbonates. Again, it's being practiced. It's already in commercial unit. Biomass fuel, nutraceuticals, these are being practiced in some of the places, particularly for biofuels and nutraceuticals. And phycoremediation, I feel this is a very important area, and probably I keep telling NERI should target this, because this is combining wastewater treatment and carbon capture all in one to get biomass. Therefore, you have a multiple option and make the economics in a big way push towards positive economics. There is a lot of DST funding available, and more than now probably 200 projects have been approved, and we have joint calls with some of the European countries, including EU and Norway, which I reviewed the last 10 years or so. And currently there are two Center of Excellence. One is from JNCSR, where Professor Peter is from, and he's going to speak on. And The industrial projects are mostly on enhanced oil recovery, biological sequestration, but geological sequestration, there is only exploratory, and there are attempts for see, enhanced oil recovery itself is partially geological sequestration. And therefore, there are oil industries are looking at it for enhanced oil recovery, coal bed methane recovery, and so on. But we don't have much open literature. That is true. And I'm happy to see that there is somebody from industry talking in this seminar. So recognize that CCUS is an important step towards carbon stabilization. A lot of activities going on. DST is funding it, but most important thing is, do we have negative emission technologies? That's the most important thing. But we need to do R&D to move towards negative emission technology. We cannot jump directly, but there are claims internationally that there are negative emission technology. We should be working, collaborating with the other institutes to towards this. Thank you very much.
Thank you very much, sir. Your very nice and crispy presentation, which mainly focus on issues like biocapture of CO2 and negative emission technology and necessity to scale up to reach the gigatons and environmental and social impact of carbon carbon dioxide storage. So these are the buzzwords, and we definitely look into this. And for information to all the speakers, as now we are having 78 audience in the auditorium.
Very good.
So thank you very much, sir, for your nice talk and sum up on the topic. And we are looking forward your guidance for all our carbon capture and climate change research. Thank you very much, sir.
Thank you.
So our next speaker is Sri Nishit N. Radia, who is the President and Chief Operating Officer of GHCL. And Radia is having a lot of experience on industry. He's having more than 30 years of experience. And Radia Sahab is going to talk on carbon capture and utilization in chemical and soda ash industries. Is a technological perspective. So now I request Madhu Sharma to introduce Sri Radia Sahab. Please.
Good morning, one and all present here. It's a great honor and privilege for me to introduce our second speaker, who is going to address the opportunities about industrial perspective, carbon capture and utilization in chemical and soda ash industries. Mr. N. Radia is the Chief Operating Officer for GHCL Soda Ash Division. He has over more than 3 decades of experience in soda ash operations and led various functions like strategy and business development, corporate quality, corporate planning, projects, and manufacturing before taking over as the Chief Operating Officer, the chemicals businesses of the company. He has been on the committees of various forums like Alkali Manufacturers Association of India and Rotary Club. Mr. Radia is president of Western Gujarat Chamber of Commerce and ex-president of Rotary Club. He is a mechanical engineer and was associated with Tata Chemicals in his earlier assignments. He is passionate about integrating the latest technological advancements in improving business processes. His literary works has been agents of social change. He has his work have ignited a fire in every heart that dares to dream. Today we are privileged to have an opportunity to listen to him this morning. On behalf of all joined here, I welcome you, sir, to this literary morning. Thank you so much.
Yeah, good morning, and thank you very much for inviting me. But looking to the speakers, I think I'm an odd man. You are all scientists, and I'm from the industry. When we are talking today, we are talking about our India has plan for the net zero by 2070, and all the companies, public and private companies, have started taking a lot of initiatives to try to achieve this target. If I talk about soda ash industry is a reasonably energy intensive energy. When we have started looking for options, normally in our industry, what we are doing is a traditional thing, making an energy efficient plant, making a different, upgrading the technology. And partly we are working on the neutralization of energy like solar, wind, and all that thing. But this will not achieve our target of net zero. So we have to look for a different option like our biofuel, hydrogen, and carbon capture and utilization. If we are talking about soda ash industry, we have one inherent advantage that we can utilize carbon dioxide. In our process, at present, we are generating and utilizing carbon dioxide. So when we are talking about this carbon capture, as I have said, we are energy intensive. We are having boilers where our flue gas is having roughly around 18%, 19% of the carbon dioxide. However, our requirement in the process is roughly 40% carbon dioxide. So this is one of the area where we can utilize this carbon dioxide, concentrating from low concentration to high concentration, and this can be utilized. We are looking for the different options also. Okay, how we do not have to generate and we can utilize more and more carbon dioxide. So this is having one of the major advantage with soda ash industry. In UK, Tata Chemicals have put up a plant where they are utilizing, they are capturing carbon, concentrating up to 90%, and then making sodium bicarbonate plant. And this is a one plant where 100% product
Arya Saab, you are not audible to us.
I think you should go to the next one and invite him.
Sir, I will contact him by phone and let us see.
Yeah.
Yeah, please. Please, sir. हाँ सर, आपका वॉइस नहीं आ रहा है सर. There is some problem in audio. You can rejoin, sir, if it is possible. Otherwise, we will continue. Yeah, I think you were traveling. That's why it may be in problem. Okay, sir. No worry. Thank you very much, sir. Okay. So there was a problem with the Sri Radia's communication because he's traveling in Mumbai, so he's not able to continue this, and we will continue the program with the other speaker. So the next speaker is Professor Sebastian Peter, who is professor in JNCSR. So he is working on inorganic materials and the capture of carbon dioxide. And actually, I known to Professor Peter by my Facebook, and he always posted his research findings and publications. So I really impressed. And I contacted him by email. So he already accepted to attend this iCEN-52 program. Professor Peter, I am very thankful to you. You rightly told that it's a very short notice because some of the programs fixed at the short notice. So definitely we will interact with you in future for a longer presentations. So Sebastian Peter is a professor at JNCSR, Bangalore. So now I request Anshika to introduce Professor.
Speaker is going to provide academic perspective in the field of carbon capture and utilization. He, along with his team, has developed a carbon dioxide reduction technology. This technology reduces carbon dioxide to methanol and has been scaled up from the lab to pilot level with a capacity of 300 kg CO2 reduction per day. This development has been awarded National Technology Award by the DST. He is active member of many prestigious national and international learned society, including Royal Society of Chemistry, ASM International, Chemical Research Society of India, and many more. He is the recipient of Young Investigator Awards from ACS, RSC, and IOP. Please welcome Associate Professor at School of Advanced Materials, JNCASR, and Founder and Director of Startup Breathe Applied Sciences, Dr. Sebastian Peter.
Yeah, can you see my slide?
Yes, yes.
Yes, okay. Is it in full screen now?
Yeah, now it is in full screen. Yes,
Okay,
please.
thank you, thank you. Thank you very much. I mean, thank you for kind introduction and kind invitation. I'm pleased to be here. It's a great opportunity to, give, what we are doing. Give a glimpse of, I would say, a glimpse of what we are doing currently here in Bangalore and around this area. So, as you can see that I'm a professor, associate professor here, and I'm also founding director of a startup company. So it's a combination of academic and industrial perspective. So we develop the material and methodology from the scratch, and then scale it up to the industry level. So, and we collaborate with both academic and industry sectors to take the technology forward. So I put this title as Scientific Strategies Towards Net Zero Emission Task, but I would consider myself as a chemist, and I'm forced to learn chemical engineering during the course of the technology development. And you see that when zero emissions by 2050, that is a target proposed by IPCC, UNESCO, etc. All the world leaders. And we in India also, Dr. Devota mentions precisely, all these, strategic plans and, how the actions being taken by various sectors, including government and private. And if you look at that, sorry. Yeah, so if you look at that, so India's, 2070, the very aggressive mode, Sweden, they're looking at 2045. And if you look at my superannuation, 2043. So we don't have much time actually. Basically, if you don't do, aggressive mode of, this one, this a CCU or whatever the zero emissions, it's going to be, beyond 2100. To be honest, I'm saying that, the way we are going, probably not sufficient enough. We have to move faster, and we need a lot of support in various sectors. So I don't want to tell much detail about the CCU, but a couple of things I just want to highlight here in Indian scenario and our the issues. So this is for those who are in the audience. You can see that this is an IPCC report, and you see that you can see that the red area, shaded area, if you are not going to take an aggressive step, it is going to be underwater by 2050. If you want to, keep that, a part of our India, when it's not in India, all over the world, but you have to take serious steps. And if you can see that IPCC, somebody attending this one, please read this IPCC report regular basis, and then you understand then what is the serious impact, I mean, of carbon dioxide or global warming, or so anything associated with, I mean, the greenhouse effect. And it is not only affecting on the geographical part, it's also affecting human body. I mean, depends on the amount of CO2 you are taking to the body. It can damage your various part of the body, when your organs, and you may end up in death also. This is a serious concern, and depends on the area. I mean, you can see that one. So what are the solutions? So you can talk about green hydrogen. And recently, Ministry of Power, they proposed 5 million metric tons per year hydrogen production. Anyway, I'm not going to the detail that part. And how to utilize this hydrogen energy or other chemical energy, converting that the chemical energy to useful, I mean, what you call electrical energy in the form of, say, for example, fuel cell. And last but least, I mean, so the carbon capture, utilization, storage. I mean, a very good overview given by Dr. Devota here. And in this talk, I would like to mention what are the activities we are doing. So for example, if you start, I mean, if you look at my web page, you can see this image. This is a summary of the activities we are doing. And if you look at that, we capture CO2 in the smaller scale, though I'm not a translator. CO2 reduction, this is a kind of in the pilot scale. And for this CO2 reductions, we need hydrogen. So you can produce hydrogen by water splitting, and there are a lot of challenges involved in that one. And this CO2, whatever we can convert by photo, thermo, electro. I'm talking, I mean, from the chemist perspective. Okay, so we can convert, I mean, that to say methanol, methane, or dimethyl ether. And you can use that methanol dimethyl ether in fuel cell, say for example in the form of direct methanol fuel cell, or hydrogen in the form of hydrogen proton exchange membrane fuel cell, and then utilize the energy in the various sectors. This is a complete package, I mean, we do in our lab. Involves, I mean, development of the catalyst and methodology development. I just want to give 2-3 examples. Very recently we published this year. So this is one paper we published in Advanced Material, where there is an IP also involved in that one. We develop a catalyst, platinum-3 germanium. Platinum is well-known catalyst for the hydrogen production. So what we have done, if you look at this structure of this one, we have different morphological position. I mean, what you call subsurfaces. We smartly designed a certain morphology, 110 crystallography. I'm not going to the detail of that one. We control synthesis in such a way, I mean, develop the material 110 or 202, and we try to understand by various in situ and ex situ techniques. I mean, so which surface is actually active for that one. So what we did actually, we introduced coined a term called Fabulous 5. That nothing but, I mean, important 5 chemical parameters that governing actually hydrogen production. Here you can see that here, onset potential, current density, Tafel slope, durability, and stability. This is a magic compound, and then it surpasses all these activities, I mean, better than the state of art, I mean, platinum and carbon. So we are in touch with an industry firm to scale up this one and develop a multi-cell, hydrogen protection stacks here. So what, I mean, my students, I mean, they try to understand why and what are the reasons, I mean, this, I mean, stupendous performance of, this catalyst, I mean, proposed germanium, I mean, leaching and then redeposition, etc. So a lot of chemistry, I mean, deep chemistry involved, I mean, to propose this one. What I'm saying, actually, we translate this one. I mean, we are in the process of translating. But I just want to say that when we have also hydrogen generation unit, similar way, I mean, at JNCSR, and we, I mean, integrate with our CO2 methanol unit and CO2 capture unit. I will come to there in detail with the capacity of 20 nm³ per hour capacity. And this is a unit, and this is based on this PEM based cell. Then if I move quickly to, I mean, how that, hydrogen can be utilized in fuel cell. We started this journey in 2015-16, and you can see that how, we tuned the structure, and with the deficiency, you can see there is an open vacant space actually, that deficiency generated, and for the ethanol oxidation, this is the anodic part of the fuel cell. And we try to modify by filling that deficient one with the nickel. Also, this is a smart design. So we try to fill with the nickel, just selectively, that ordered nature, and then try to improve that one and ethanol oxidation. So we continue this journey, and then this year just we published a paper in JAX. I mean, so we feel that the deficiency with the platinum, And all of everybody feel in the community, I mean, so platinum is active species for, I mean, oxygen reduction reactions, I mean, at the cathodic part of the fuel cell. But we proved that one, it is not actually by various methodology. It is tuning the palladium by the introduction of platinum. What we achieve here, it's a complete, I mean, almost complete electron transfer in the cathodic part. Nothing but, I mean, 4 electron transfer, and then you got this, I mean, again, I mean, again, an extraordinary performance, and this is validated by various in situ techniques, I mean, including in situ XRs, IR, etc. and all. And again, another patent involved in this one as well because of the extraordinary performance of this one. So, and we have the capability. I just want to emphasize the point that whatever we develop that fuel cell material, we are what you call making a membrane, and we can test that single cell in our capacity, proton exchange membrane fuel cell and direct methanol membrane fuel cell. In fact, we published a few papers, and another 2 patents also involved in that one. So I'm now coming to the theme CO2, and those who are students or those who are in the early careers, I mean, CO2, I mean, I also knew that CO2 is nothing but a linear molecule. But if you look at that, carbon has it's an electropositive in nature, and oxygen is an electronegative in nature. And because of that one, a slight, I mean, the charge distribution, the oxygen becomes nucleophilic, and carbon becomes electrophilic in nature. So this is the fundamental of a scientist to understand how efficiently this is very stable molecule, efficiently can convert, okay, dissociate CO bond this side and hydrogenate, and you get, I mean, methane. If you dissociate both oxygen bond, or even if you dissociate only one oxygen and then end up in CH3OH and by hydrogenation. So for that one, we have to design the catalyst in such a way, either it should be electron rich. If it is an electron rich one, carbon will be absorbed at the surface of the catalyst. If it is an electron deficient, oxygen will be absorbed at the surface of a metal. So this is a basic knowledge, and you have to visit, I mean, a lot of fundamental things like thermodynamic parameters, how you can efficiently convert, I mean, methane or methanol or other carbonates. I mean, say for example, there are 2 mechanisms involved. One is the no change in oxidation state, that nothing but the carbonates. You can see the delta G parameters, very easy to convert. But if you look at, I mean, methane and methanol, there is a change in oxidation state. I mean, it's not easy to convert. You can see this number here, minus 166, minus 162. So for that reason, we need high thermal energy for the conversion. So there is a requirement of extra energy input for the conversion. Make this process is not that easy. Because of this reason, economically, these processes are still not a viable process. So this, if you don't understand this fundamental knowledge, you cannot develop the catalyst. There are a lot of papers, I mean, how to design the catalyst. This is a paper, I mean, published, a theory paper, Progress in Surface Science. You can see that if you take a 1 metal, or 2 metals, or if you take a 3 metals, or if you take a 4 metal, somebody, I mean, maybe criticize, I mean, outside of the metals and say, why you are mixing all these metals together? What is the role? But there is a reason behind that. So you can see that you have to bend the CO2 in such a way carbon is absorbing, or you have to in such a way all, I mean, carbon, oxygen, it's a different metal. It depends on how their bonding nature. It can be dissociated, this M2O, M1O, M3O, and that depends on how you design. You can end up in different products. Okay, so if you look at C1 product, CO2 to formic acid, CO, formaldehyde, methane, or methanol, anything can form. If you are targeting methanol, you cannot eliminate carbon monoxide. If you are targeting methane, I mean, you may end up in CO again. So this is a difficult task to get 100% selectivity. This is just a C1, just got a C2. It is even difficult. You can see that it can go through ethylene pathway, or it can go through ethanol pathway. You may end up in glycoldehyde, ethylene glycol, ethanol, ethylene, acetaldehyde, acetic acid, I mean, glyoxal. Anything you can think about carbon products. So just imagine if you go to C3 product, even more complex. In that C3 product, it involves C2 and C1. It's extremely challenging task whether you can produce a selectively, I mean, one carbon-based product from CO2. So what we have done, lot of synthesis strategy using, this is one paper published and beautifully, I mean, summarize what are the methodology. In fact, I mean, this methodology, even beyond that one, we tune in our laboratory, I mean, to tune the activity. You can see that the performance, and then, the increasing activity, either it's intrinsic or number of active sites. You can tune the catalyst in such a way to selectively. So what we have achieved in JNCSR, you can see that either thermocatalytic or electrocatalytic and photocatalytic, we produce all these chemicals. Okay, we have even producing more and more. I mean, so starting from acetic acid or anything. I mean, you can talk about ethylene. Each one has its own niche mark actually. If you can take it forward, I will show a couple of examples here. This is one recent advanced material paper we published on CO2 to methanol by electrochemical pathway. What we have done actually, we selected a couple of intermetallics based on the knowledge from the database. One is copper gallium 2, another is copper 9 gallium 4. I just briefly mentioned this one. So copper gallium 2 is a tetragonal system. So we had an intuition. So copper gallium is a tetragonal system. We know that copper 9 gallium 4 is a, or the cubic system. It is a 3-dimensional system. Because of copper gallium 2 is a 2-dimensional system and surface is exposed to gallium, we can selectively oxidize gallium to gallium oxide. So that gallium oxide is well known for CO2 methanol. It is well reported. But the idea is actually, if you can make a skin layer of gallium oxide at the surface during the operandi conditions, the activity can be improved. In fact, our the proposal actually validated by electrochemical cell. This is a H cell type, and you can see that at the lower potential, if you look at this number, I mean, in this blue one, almost an 80% of Faraday coefficient. This is the highest ever Faraday efficiency reported in the literature, that by copper gallium 2. On the other hand, you can see that copper 9 gallium 4, the Faraday efficiency close to 40%, which is what it says actually. I mean, we did, a lot of operando studies like in situ IR. I mean, you can see we have the facility here. And the CO2 to methanol, either path 1, as you see here, or path 2. So if you see, this intermediate in IR, this is validating. What we saw this IR, you can see that 15, 19 and 13, 73. And you are seeing these two intermediates. That's nothing but path 2 is actually going through. So path 1, not 1. So we propose the mechanism in such a way that in situ techniques, not only in situ IR, we have the capability of in situ XRD, in situ Raman, in situ EPR studies, and then we are also doing, in situ XAB studies, various beamline, and here you have example. So here also we proposed, in situ XABs. What happened actually, copper edge or gallium edge, you can see that in copper there is no oxide formation, but in gallium you can see that there is a gallium oxide formation. That's validating. Gallium is actually forming during the operation condition. And then we calculate the percentage of gallium oxide, at a different potential and validate. I'm not going to the detail. And this paper, published almost 1.5 years, in a review process. And we set up, in an in situ cell for the, measurement at Petra. And what we found that there is a gallium oxide formation. And also we notice, it's a copper oxide formation. It is actually protecting this, surface, and it's validating. This is what, we are done. And during this process, we publish another paper, SES Nano, again this year only. And if you do that, in a flow cell, whatever I did it in a cell, and then flow cell, you can improve the current density and Faraday efficiency. And we took this model in this one, and we designed a flow cell. You can see that this is a flow cell designed by my students. And then it took 6 months actually, and the various parameters like catalyst design, nature of electrolyte, potential, process parameters, etc. and all were designed, and then they just could reach the Faraday efficiency. You can see that methanol here it's close to 80%. What we improved here is the current density. This is one of the challenges. If you don't have the current density, neither the big journals accept the paper nor the industry will take it. So we have validated for this current density by using the flow cell, and over a period of 24 hours the stability was excellent, and this is the highest Faraday efficiency at a lower potential reporting in the literature. How many minutes I have? Hello?
10 minutes.
Okay, fine. So what we did actually, during this course, we published several papers. You can see that one CO2 to methanol by photocatalytic pathway, CO2 to formic acid in SES energetics. We controlled the systematic assessment of, this one. And CO2 to methane by strain relaxing, so the system by introduction of the heterostructure. We found a series of, if you look at all these peppers, so what you see that CO2 to C1, methanol is a C1, formic acid is C1, and methane is C1. I invite students to read the peppers. Let's try to understand. We propose a lot of chemical insights. So to understand how to design the material, for the CO2 reduction. So we jump ahead to the next level, CO2 to ethanol, and we publish this work in Energy and Environmental Science, one of the very difficult journal to publish actually. So what we have done, we design a catalyst, a combination of red phosphorus, this is natural abundant material, and bismuth molybdate. So we varied this composition such a way to tune the band gap and band edge position. As you see that on band edge position of red phosphorus based on our experimental valence band and conduction band, with a band gap of 2 electron volt, and then this bismuth molybdate. So the point is actually if you use only red phosphorus or bismuth molybdenum oxide, and we cannot use that one. One is actually we cannot absorb the light. Second one is actually charge recombination by photocatalytic. So I'm talking about here photocatalytic pathway. So then we designed this one. So first we excite this electron, and then followed by this excited electron without recombination, that either by type 2 mechanism or Z-scheme mechanism, we can transfer the electrons here, and the potential is arranged, and you can see that this one methane, if it is a minus 0.24, methanol or ethanol is minus 0.3. So we design in such a way that valence band position is the 0.33 to have this ethanol production. That's what all this game together we did it. We varied the compositions of composites 1:1, 1:2, 1:3, etc. and then we tested the catalyst. So you can see that this is a very simple sonication method, and we have a nano phosphorus and the nano rod of bismuth vanadium. Yes, sorry. Yeah, so then sonication period we varied. You can see that when this ethanol formation after 20 minutes of 20 hours of sonication, it is around 55 mole per hour per gram. Again, this is the highest ethanol production by photocatalytic pathway. The best reported is around 22 molar per hour per gram. And what my students did, they did this experiment under sun in different climate, starting from, you can see that April, and then it is December, it's a December, and then January and March, and then June, at different condition, under sun or cloudy condition or rain conditions, and then just produce ethanol under sunlight. And you can see that one, and at different conditions, the production rate is actually close to 30-35. That is remarkable. And then they cycle also various conditions. We could able to produce ethanol in the continuous process, and catalyst is also stable. And not only that one, so just again we went back. What is the mechanism in detail with the support of IR or in situ IR, in situ EPR, in situ XHAP studies, and then we propose ex situ XPS study, and the DFT calculations at various intermediate and energy of each intermediate involved, and we propose the mechanism in detail. So this is a business we doing actually. Recently we produce ethylene, a paper is under review, and we produce butanol, we produce olefins, we produce a dimethyl ether. These are all work actually under revisions in high profile journals. Probably you may see those papers very soon. So finally, we produce methanol and isopropanol. Another work is actually, we are N-propanol. So we are, we have the paper under review. So what I want to say that now, so we have developed all this material. So that not stopping us to take it forward. So how we can translate them. So this is one thing we have achieved, a translation of CO2 reduction to methanol. We started, a company, in 2016, and then we have a lot of recognitions. You can see that one. We were selected as the National Technology Award by Government of India, TDB and DST, and Karnataka State Government selected. We were in the final of Carbon X Prize, $20 million. Only Indian, one Asian team in the final round of competition, and we got the winner of, we were the winner of KPMG, decarbonization. So finally, I would like to mention that this technology that we have developed, this is a thermocatalytic.
Madhu,
Yeah, so then this is commissioned first plant in Telangana with a capacity of 1 ton of CO2 per day capacity to methanol. As Dr. Devata mentioned, so we are capturing CO2 from the chimney, purifying, producing hydrogen on site, and then reacting hydrogen and CO2 and the reactor and producing methanol with a capacity of 1 ton approximately. So this is the integrated technology we developed in JNCSR. At the various part, you can see that fuel cell, we have the reactor, CO2 capture. CO2 capture is partner basically. We integrate them and we produce hydrogen with a larger capacity, 20 nm cube capacity, and then we already integrated with partner in Tuticorin, and then we are aiming actually for the revenue very soon. So these are the various part of the technology, CO2 reduction unit that we have in JNCSR, and starting from the building to the methanol production 12, number 12 control production. We have done, this is validated by various national and international agencies. We have the ISO certificate, we have life cycle analysis to, that endorsed, this is done by University of Calgary life cycle analysis, LCS certificate, we got it from US firm, Southern Research. This is also validated by, BPCL, Shell, etc. And we have the unit, and currently, so we are actually moving, to a new location to expand this one. And the cost is very important. With our technology, we can produce approximately 12 to 15 rupees per liter. The market value in the range of 25 to 35 liter, Indian rupees per liter. And this is a plant I was mentioning about. So last but least, we have one of the first center of excellence in JNCSR, and this is already mentioned by Dr. Devota and others also. And this, we are looking for the combination of academic and industry, both in science and engineering, technology transfer, networking, economic analysis, life cycle analysis, outreach, and those who are interested, please, write to me. We are happy to support you, and students also some training, but some basic knowledge, some experience would be recommended, to guide you. And then if you can set up in a lab in our side, we are happy to support you. Our knowledge, we can share with you. Already, there are few people in touch with me. Some students also visiting us to learn this technology. So now we put a few questions, technological challenges. As a chemist, can we mimic natural artificial synthesis in the lab? Can we convert CO2 on the not moon surface, Mars, I would say, surface to food? There was a competition from NASA CO2 conversion challenge, and it was actually finished, but I don't know how successful it is. It is a very challenging process. In fact, I was a part of that competition, but I just later pull out and because of technical difficulty. So then can we convert CO2 to a lot of, say, for example, diamond in the lab? Or can we convert CO2 to jet fuels? This is one of the biggest market, olefins or jet fuels or hydrocarbons. Can we do that one? These are the technological challenges we are going to face. So we need to have very aggressive mode. We should not even think about 2050. We should think much before that one. With this one, I would like to acknowledge all the people involved, particularly Professor Rao, from the day one, and still he's helping, and never said no to me. And my team, students, this is my current students. I have a lot of students involved in that one, a lot of funding agencies also involved. And thank you very much. Happy to answer the questions if you have.
Thank you very much, Professor, for your very nice presentation touching the fundamental aspects, how catalyst functions and mechanism, and especially we are very much interested on converting the fundamental science into application side. Is very appreciable. So any technology stand still once it is a fundamentally very strong. So hopefully we definitely in touch with you, and once again very thankful to you. And question and answers part will be there. Now to the all the speakers. Now we are having 111 participants in the audience in the auditorium. So this is for your kind information. So now I request the fourth speaker. So she generally do not require introduction and well known to everybody in the field of carbon capture studies. And she is Dr. Sadhana Railu. She's heading the Environmental Materials Division in CSIR NEERI. So I request Madhu to introduce Dr. Sadhana Railu.
Thank you, sir. Our last but not the least speaker who is going to deliver a talk on CCVS initiatives of CSIR NEERI, Nanophotonic and Biomimetic Systems is Dr. Sadhana Railu ma'am. She is a scientist and head of Environmental Materials Division of CSIR NEERI. She is spearheading the research related to materials and catalysis in the area of energy and environmental technologies. He is leading the team of green firecrackers and has made significant contributions in developing new formulations with reduced emissions and also contributing towards related legal policy interventions. She is coordinating various bilateral international programs and collaborations, including Indo-Korean, Indo-UK collaborations, Indo-US, and has also visited these collaborating institutes. She has worked with multinationals like Horizon Fuel Cell and several industries in India, including NOCL, Rudraksh Chemicals, NTPC, ERA Agrotech, etc. She has to her credit the Best Presentation Awards and other local and institutional awards for material developing, including CSI Technology Award for Green Firecrackers and Vaspik Chemcon Award to her new pay. Today, we are privileged to have an opportunity to listen to her this morning. On behalf of all joined here, I welcome you, ma'am, to this literary morning. Thank you.
Thank you, Madhu, for the nice introduction. Well, can you see the slides?
Yes, madam.
Yes, ma'am.
Okay, very good morning to you all. I shall be giving an overview of the CDI initiatives, that is the cross-disciplinary initiatives that are being pursued at our institute with specific reference to the nanophotonics and the biomimetic systems which are being put into use for carbon capture, sequestration, and valorization. Well, this is the outline of my talk today. I'll briefly touch upon the genesis of CDI with reference to CCUS or CCVS, then touch upon the energy and environment nexus, which is very much relevant as far as carbon capture, valorization, and sequestration is concerned, and then highlight the activities which are being pursued at our institute with respect to CDI, that is cross-disciplinary initiatives, wherein we are integrating solar energy, biological systems, and waste management with carbon capture, valorization, and sequestration. So coming to the genesis of cross-disciplinary initiatives, well, cross-disciplinary initiatives, as we are all aware, implies combination of two different disciplines. It could be chemistry and biology, or similarly, it could be different approaches which can be combined, and they are normally looked into as hybrid technologies which are to be developed to address issues of kinetics, footprint, energy footprint, a combination of energy and environment footprint, so on and so forth. So, as I've already mentioned, these are the three approaches which are shown over here, which are being pursued at our institute, basically to minimize the energy penalty which is associated with carbon capture and also to improve cost effectiveness. So energy and environment is definitely an emerging strategic issue which is being addressed across the globe for improving the quality of life and of course maintaining it as well. Well, there are different approaches which are being pursued, and if we categorize it, there are two-pronged approach which is being thoroughly pursued. First is the identification of hotspots and deployment of interventions to make the systems energy relevant. Well, when it comes to thermal power industry, this issue of energy and environment is very much relevant, because when we are going for coal or carbon-based generation, we inevitably have a lot of environmental issues as listed over here. We are generating solid waste like fly ash, There is liquid effluents from the coal washeries and the ash ponds, and of course the flue gases. Now the issue is, when we are generating energy, we have these environmental issues, and when we look into addressing these environmental issues by developing energy technologies, then we inevitably end up with using a lot of energy. Now, how do you address these issues? So these are the two-pronged approaches which are being pursued now. First and foremost, the hotspots and deployment of interventions to make the systems energy neutral. And how is it possible? Is there a possibility of using solar energy in this case, so that we reduce, and to some extent we make the system energy neutral? Secondly, there is a possibility of using the embedded energy, which is inevitably associated with the waste. Let's take the example of fly ash. Fly ash is being handled by several ways. We are all aware of it. It's being converted into cement. At our own institute, we converted fly ash into zeolites, which are very, very promising material. We have about 10 odd patents on that. But there is an embedded energy associated with it in the form of silicon and aluminum. Now, the issue is, instead of applying energy and converting it into some other product, can we use that energy to derive energy out of the waste in the form of silicon and aluminum, which I'm sure most of us are aware of, has a lot of energy related applications. So these are the issues which are being pursued with respect to the thermal power industry. And when it comes to carbon capture, valorization, and sequestration, our institute has been carrying out R&D activities in this area for almost more than a decade, more than 1.5 decades. And at this point, I would like to acknowledge the guidance and mentorship of our ex-director, Dr. Sukumar Devota, who actually introduced us to the topic, taught us the basics of carbon capture, valorization, and sequestration. And this work is being continued at our institute since 2007, I believe. So when we talk about the different R&D activities, we've been working on carbon capture, developing different kind of materials, addressing the issues when it comes to carbon sequestration. As already mentioned by Devota sir, we've been working on algal, and I'll be touching upon the enzyme-based sequestration, which is being carried out. And to some extent, we have been focusing on carbon valorization as well. Well, all these activities were carried out as part of different projects which were funded to us by industries and different ministries. So I will start with carbon capture and energy penalty. As it has already been mentioned, aqueous amine scrubbing is the benchmark carbon capture technology. However, it is very energy intensive by virtue of the fact that the CO2 recovery step consumes about 50% of the overall energy, with obviously very negative implications, in the sense that the energy penalty for CO2 removal is around 0.2 to 0.5 megawatt per hour per ton of CO2, which has implications that it leads to an energy requirement of almost 20 to 30% of the power plant output. Obviously, this leads to high capital cost. Along with that, there are a lot of issues associated with the amine solutions, like it causes corrosion, on degradation and evaporation. It generates a lot of pollutants. So all these points which are listed over here underscores the need for developing technologies to minimize the energy penalty and improve cost effectiveness for carbon capture. Well, with this in background, these are the activities. These are just glimpses of different activities which are being carried out at our institute, and I shall be majorly focusing on two aspects. First is the biomimetic carbonation reaction, wherein we are trying to pursue a natural process of carbonation or sequestration which is happening. Here, we have tested it for different applications like generation of calcite, generation of CO2 and hydrogen, then engineered mineral weathering, so on and so forth. So in solar energy applications, we have been focusing majorly on solar carbon capture and solar fuels. And these are some of the systems which are shown over here, which have been developed and designed by us, which has led to very focused and high impact factor publications like in energy and environmental science, GMC, applied CAT B, so on and so forth. I'm not going into the details of this, and has also led to several patents and design registrations. And I've already mentioned all this work was sponsored to us by national and international industries like NTPC, Alcoa, and of course DST, DBT, so on and so forth. Okay, so I would be touching upon three aspects, in fact, two aspects as per my topic. But I'll briefly also touch upon how we are integrating waste management with carbon capture and sequestration. So I'll be touching upon the hybrid technologies based on solar energy driven carbon capture, and then hybrid technologies based on integration of biomimetic systems with carbon capture. So coming to hybrid technologies for solar energy driven systems, as I've already mentioned, MEA is one of the most promising systems, but it is becoming increasingly unacceptable because of the energy penalty which is associated with it. Carbonate systems definitely offer a lot of potential, and they have lower heat of generation. The energy penalty, as I've already mentioned, is majorly because of the high energy required for regeneration. In this context, carbonate systems definitely offer potential, as can be judged from the heat of reaction, but they have slow kinetics and therefore require high temperatures and pressures. So these issues can be addressed to some extent by using solar energy, which is what we are pursuing at our institute. Well, why, what, and how solar energy, we are all aware of. This is the tune of energy which is available with this. This is our global demand. So 10,000 times of current world requirement. Sorry, solar energy is available 10,000 times as compared to our global energy needs. And these are the statistics with respect to available of solar energy in our country. I'm not going into the details of it. So this basically illustrates why we should be integrating solar energy with carbon capture to make the systems carbon negative, or at least carbon neutral, and more cost effective. So in this context, two approaches are being pursued by us. We are directly using the solar thermal heat by using the different systems like the concentrators, the furnaces, so on and so forth. And most interesting and unique aspect is harvesting the heat of PV panel, which I'll touch upon very briefly. Then we have focusing on how nanophotonics or how plasmonics can be put into use for efficient regeneration of solvents. So these are some of the systems which have been designed by us, wherein the concentrators can generate steam which can be retrofitted to the MEA stripper to look into the energy penalty, or there can be in situ steam generation by using the nanophotonics. This is a unique design which has been developed by us. Typically, the panels are associated with a lot of issues related to heat islands, because when the panels are subjected to the UV as well as the IR, which is not taken up by the panel because the panel essentially takes the visible light, it generates lot of heat, which is not good for the life of the panel. And at our institute, we have developed a novel concept of BBC, that is broadband absorption cell, wherein by using different combinations of coatings and materials, we are able to harvest the UV and IR and convert it into heat, the heat of which can be put into use for carbon capture. I believe this is one of the unique approach as far as solar carbon capture is concerned, which is being pursued at our institute. The second very interesting report was by Khan and et al. Way back in 2014, where carbon nanoparticles were put into use for stripping CO2 from MEA. And as can be seen in the figure, there is a huge difference in CO2, which is evolved when we are treating MEA having carbon particle as compared to the systems without the carbon nanoparticle. This was a very, very interesting report, which prompted me to explore this option of using nanophotonic particles for regeneration of solvents, and the work is pursuing at our institute with very, very interesting results. Well, in this context, plasmonic materials or the nanophotonic materials have very, very important role to play. And I'll just touch upon very briefly what plasmonic materials are all about. It essentially has the plasmonic nanoparticles, and they are very promising materials in the sense that they can convert solar energy into chemical energy by virtue of a very important property, that is surface plasmon resonance, which is collective oscillation of conduction band electrons when exposed to electromagnetic field of incident light. So these metal nanoparticles definitely have to be UV absorbing, visible absorbing like gold, PT, so on and so forth. But besides that, lot of efforts are being made to make it broadband material so that it can take care of the UV visible and IR as such. The important aspect is that when excited on resonance, these metal nanoparticles, in which case the energy which is not being re-radiated through light scattering is dissipated through Landau non-radiative damping, which leads to dramatic rise in temperature in the nanometer scale vicinity. It has been reported that it can increase the temperatures of water well above 100 degrees Celsius. So this was very interesting, and these reports were given first by Halas et al. And our group from Rice University. And then later on, we developed a library of plasmonic materials, and we've been working in this area with plenty of publications since 2010. We have developed plasmonic materials for photothermal heat, which is based on carbon, then plasmonic metal, MNP, metal oxide based composites, then materials based on zeolite, so on and so forth. I'm not going into the details of this, but these materials have huge applications as far as carbon capture and sequestration is concerned. One very promising material was based on carbon material, which is a carbon plasmonic composite. This work was reported way back in 2005 in Energy and Environmental Science, wherein we have established the proof of concept for photothermal heating of alcoholic solutions. This work was carried out jointly with Professor Didi Sharma from ISC. So this is with respect to photothermal regeneration of solvents. We were sponsored a project by NTPC wherein we were trying to develop different kind of materials for carbon absorption. And I'm showing the results of one very promising material. It was based on zeolite at that point of time. So this work was carried out somewhere in 2010. And you can see that by functionalization of zeolites, we were basically able to address the issue of making the materials more selective and making it work in the presence of water, wherein the absorption capacity declines significantly. By virtue of these two reactions given, in presence of water, the CO2 reacts with amines to form the carbonates, and in absence of water, it reacts with 2 moles to form carbamate. So based on this, different materials were designed by us for aminated materials. And in this context, a very low cost fly ash based zeolites were developed by us. We have several patents on this. This material has the potential for incorporation of metal nanoparticles like copper, nickel, etc., which can give us the plasmonic in situ heat generation for aminated as well as non-aminated materials for regeneration, basically to reduce the energy penalty. So those are the some of the activities which are being pursued by us, basically to reduce the energy which is associated with the regeneration. And there are some systems in which we can accelerate the rate of reaction by using catalytic approach. And in this context, these biomimetic systems have been looked into at our institute. Now, there's a very promising enzyme, which is carbonic anhydrase, which is functioning in humans and other living organisms to facilitate efficient CO2 transfer during respiration. So based on this carbonic anhydrase, different kind of catalysts were designed by us, which included the heterogeneous CA-based catalyst, wherein we are immobilizing it and also developing stabilized enzyme nanoparticles. Besides that, we are also focusing on developing mimics of CO, wherein zinc is the active center. These catalysts, which have been developed by us, have been tested for calcite production. They have been tested for engineered mineral withering, and most importantly, they have been tested for carbon capture with recourse to value addition, that is generation of hydrogen enriched gas. So coming back to the mimicking process, if you see the carbon dioxide transport in blood, it happens by by dissolution of CO2 in the blood. It happens by the carb amino compounds, but the most interesting, as I've already mentioned, is that it happens by a biocatalysis process in which the enzyme is put into use. What's happening is that the CO2 hydration reaction happens, which typically happens in water as well, but in the presence of the carbonic anhydrase, it increases a million times, which is very, very interesting, because in this case, we can avoid the cost-intensive CO2 concentration and transportation step. And here we are not only doing carbon capture, but we can convert the bicarbonate to calcite. So it is a site-specific solution to carbon capture and sequestration in one go. So this was very interesting. We have developed a lot of immobilized and stabilized catalysts, and all this work has been reported since 2009. We have plenty of patents and publications. This work was funded to us by DST, DBT, and several other ministries. But very recently, I came across this very interesting aspect. We were invited to join this scaling up activity by the alcohol industry, considering the expertise which we had in the CA. And later on, it was published that CO2 solutions and Carbozyme, along with alcohol industry, have tested this concept for amines, which has resulted in 90% reduction in the CO2 absorber column with a low energy solvent like MDA, which is methyl diethanol amine, which is a tertiary amine, and it is being tested for different solvents like MEA, so on and so forth. So with the expertise which we are having in this area, we are trying to use the different catalytic materials, the mimics, etc., for looking into this issue. This again is a very, very interesting aspect. This was reported by Columbia University as engineered mineral weathering. We pursued this work further and differ considerably with what has been reported by this group by virtue of the fact that instead of using chelating agents over here, we have retrofitted the systems with hybridized electrochemical and biomimetic systems in which the protons which are being generated during this hydration reaction can be separated and can be used for dissolution of minerals like serpentine, which releases the silica, which can be removed by liquid and solid separator, and the magnesium ions which are being released can react with the carbonate coming from the CO2 hydration reaction to form the calcites, which are value added products for the paper fillers as well as the construction materials. So this is a novel process which has been developed by us. We've been talking a lot about soda ash, so I thought this is an interesting work which can be looked into. Fly ash, as we all know, is the waste coming from the thermal power industry. We can extract sodium silicate, and when we pass CO2 through it, we get the sodium carbonate as well as the SiO2. Now, this soda ash can be put into use, and SiO2 can be taken up further for extraction of silicon. That is the embedded energy which I was talking about. Now, coming to the last part, that is carbon capture with recourse to value addition. This work was carried out way back by us. Now we are going, proof of concept was established. Now we are going into the translational mode. This has also been discussed by Professor Sebastian, so I'll not go into the details of this, wherein a closed loop cycle is being pursued for carbon capture and recycling, wherein the hydrogen is coming through renewable energy, majorly from solar, to reduce carbon dioxide to methanol and other products which can be put into reuse like DMC, methanol-based fuel cells, so on and so forth, so that it becomes a closed loop cycle. Well, at our institute, we are following a different approach. From hydration reactions, the protons generate the hydrogen, the carbonate is being separated by using a anode which can generate calcite. This is the first approach which is being put into use, wherein we are hybridizing electrochemical and biomimetic system. In the second approach, we are using photoanodes which will generate the holes and the electrons. The electrons can be put into use for reducing the protons to hydrogen. And of course, the calcite can also act as a donor and can be precipitated in the presence of biomimetic approach. So this is essentially hybridizing those systems. And lastly, we are working on transforming wastewater treatment to carbon negative and energy process, in which the raw water or the sea water can go into this. If it is raw water, the organics will generate CO2, which will be supplemented by additional CO2 to generate hydrogen and carbonates. This has been tested, and we have been able to generate CO2 based solar hydrogen, CO2 based hydrogen enriched fuel gas, which can be put into use, or the fuel gas which is having CO2 and other like nitrogen and other things associated, they can be subjected to separation. We have done that, and we could achieve hydrogen evolution rate to run 10 and 30 watt fuel cell at our institute. So I would now like to summarize. We know that nature has its own process to tackle pollutants by marine sequestration, humidification, photosynthesis, carbonation, which I've already talked about. And all this was in place prior to industrialization. But post-industrialization, the levels of CO2 have exceeded to a level where these natural processes are not able to control the CO2 levels. The solution probably lies in biomimicking these processes, which is what we are doing as far as carbonation reaction, as far as artificial photosynthesis using photocatalysts, so on and so forth are concerned. So as future perspectives, we have proposed a COE basically for translational research, wherein we want to convert these proof of concepts and understand the scaling up, the piloting issues which are there with respect to using the nanophotonics and the biomimetic systems for addressing the issues related to carbon capture and sequestration, essentially to make the processes carbon negative and more cost effective. Besides that, there are some very interesting reports on visible light triggered carbon capture release of CO2, as well as dynamic photo switching in metal organic frameworks, which is being looked into by my colleagues. We have developed some very smart textiles and coatings based on some of the novel materials which I've already described. We can pick up CO2 from the ambient, and these systems are very much in place and being tested at our institute. Lastly, I've already acknowledged my sincere most thanks and acknowledgements to Dr. Sukumar Devata, our ex-director, for his guidance and mentorship. As I've already mentioned, he taught us the basics of what carbon capture valorization is all about. Then my sincerest thanks to the different CCVS programs, mega programs, in fact, which was funded by DST, DBT, and TAPSON program, which was our in-house program of CSIR. I acknowledge my collaborators from different universities, as well as our national collaborators and all the sponsors, including the industries and various funding agencies. This is the team which has contributed to the different work which has been presented by me. Thank you all for a very patient listening, and I would be very happy to address some of the questions if raised by you all. Thank you.
Thank you very much, madam, for your nice presentation related to an array of materials and processes developed mostly from the waste, which is highly inspired. And we are, and also biomimetic systems, which you are explained in a briefly, is a very interesting one where we can mimic the natural systems in future. So thank you very much, madam. Now we are having a question answer session where we received few questions from the audience. So right now we are having 112 audience in the auditorium. So we received the questions. So now the questions will be the clarification or questions should be asked to the concerned presentation. So in the absence of Nishit Radia, that may be answered any one of you, I think so, if it is. So now I request the questions taken by the Madhu Sharma, Anshika and Sunita. So please read out the questions you are taken from the audience list. Madhu Sharma.
Good afternoon, everybody. One question that is addressed to Dr. Sukumar Devota. Sir, among the various challenges under carbon capture, according to you, what are the constraints in commercialization of the solid adsorbents for carbon capture application at commercial level?
You see, solid absorbents are being used in real demonstration. It's not that, but only thing is, as I said, there are certain things like for your direct air capture, people are still using solid absorbents. They're not using any amines. So it is being used. And you have to do your calculations for net emission. See, in most of the current projects, demonstration projects are not carbon negative yet. They are doing it because we need to learn to go towards carbon negative. You cannot say it has to, only if you prove carbon negative today, you can proceed. No, we have to learn. We have to go down the learning curve. And therefore, people are still using all kinds of separation techniques to learn, to demonstrate, to reduce the cost. So I can't say that for instance, MEA is the most difficult one in terms of energy, but most of the demonstrations are still using MEA. Okay.
Okay, sir. Thank you.
Next one.
Thank you everyone for the informative talk. My question is to Dr. Sukumar Devata sir. Sir, my question is, how can we reduce parasitic energy required during regeneration of spent solvents?
Yeah, that is why people are looking at mixed solvents. MEA is the best in terms of capacity, but it is in terms of parasitic energy, it is the worst. So you start going towards secondary and tertiary. So get into mixture of solvents to reduce. So in solvent based, people are looking at promoters along with mixed solvents. And what is being used in some of the demonstration in India is also mixed solvent. So that is one way. But in terms of absorption and other techniques, again, you have to look at how to promote uh, absorption at low cost, low energy, and then release of CO2 at low energy. These are challenges, but then you have to learn. You have to learn using, like we are, Sadhana Rai, you mentioned about carbonic anhydrase. That is one way of promoting carbon capture. But at the same time, you have to look at how to decrease the desorption. So all these things are still going on, and most of the demonstrations are looking at this reduction in parasitic energy. Thank you.
Thank you so much, sir.
Thank you all for this informative talk. My question is to Professor Sebastian Peter. As most of the flue gases have high temperature and moisture content, such cases, how do we target selective absorption of CO2 from other gases?
Yeah, thanks for the question. In fact, I have written a review article, this published just now in JMCA, CO2 capture under humid condition. This is one of the technical challenges. The humidity, humid presence can, decompose the material that being used for. So we have the selection of materials, narrowed down because of this issue. We cannot use all the material that is being used for the dry conditions. This is one of the concerns you have to see that, but it is seriously, it is possible. It is being, practiced by several industry where the humidity is high.
Add something to this?
Yes, please.
Sure. As rightly said, humidity is a very big issue in flue gases. It is, we have moisture to the tune of about 4 to 5%. So to address this particular issue, efforts have been made globally and of course at our institute also to aminate those materials so that the selectivity is imparted towards CO2 as compared to water which is there. And this concept has been tested by aminating different materials. And as I had presented that typically the absorption capacity dropped by a factor of 2 for non-aminated material in the presence of moisture as compared to the aminated materials. So this could be one of the way out to as far as moisture.
Yeah, I agree.
Thank you for adding. That is, yeah, absolutely agree.
Thank you, sir.
Thank you, ma'am. Thank you, sir. Another question is from the audience side, which is to Dr. Sebastian Peter, sir. If the flue gas is a mixture of particulates and gaseous components, how can you address catalyst poisoning by particulates? Sahata?
Nice. Again, similar questions, but different problem here. So particulate matter can actually damage your, processing. If you want to utilize them, number one. So where the major challenge is actually how to remove that one. See, again, it is already practiced by CO2 capture industry. How to remove the particulate matter. If you don't remove, you end up in, say, for example, I can tell you, especially CO2 utilization, it can end up in coke formation and it can build the pressure and it can actually, the durability of the process also can be damaged. So one such one problem we are identifying in the current setup we are building in Telangana. The particulate matter is high. So if we filter them by special material and then, selectively, capture the CO2 and purify the CO2, even sulfur dioxide, another problem. First we started with the humidity, just one particulate matter, the third part is sulfur, and the fourth part is oxide of, the nitrogen. So these all, the material design strategy. Still, although it's mature technology, as, Dr. Raila mentioned that one, so again, the material design strategy or methodology design strategy, still we are working on that one, but it is another problem. Agreed. And as a CO2 utilization person, all this will damage my catalyst during the process of CO2 to methanol or CO2 to any chemicals and fuels. We have to have a high pure CO2.
Maybe we need to preheat before getting into the system. So that would
Yes.
Yes. Pre-cleaning is a must.
Yes.
In real life situation, pre-cleaning is a must.
People talk about, okay, point source CO2 conversion. I mean, I don't know how to do that one. It is, there's a call from ACT. One theme is actually point source CO2 conversion. I would say you have to clean and conversion into the point source. That is only the option.
Yeah, that is the only option. There is no other option. If you are going to large single point source, you have to do cleaning for particulates,
Yes.
for say a SOx and NOx. Keep it to a lowest level. Anyway, the environment requires before release certain levels of DSOx and DNOx. So you have to do that. Only thing is the material you develop should be still be able to tolerate some residual SOx and NOx. It cannot be totally, it will have, you cannot bring it to zero.
Yes.
It should be still, should be able to tolerate certain level of, that's where you need to find out what is the threshold of the material you are developing. Yeah.
I just want to add one point. The earlier question, humidity. Sometimes you don't have to worry about humidity up to certain extent. Say, for example, CO2 to methanol. The material we use oxides, alumina or indium oxide. Alumina is, in a state of art. Copper, zinc, alumina. It's a small amount of humidity. When you treat with a catalyst, this alumina or whatever the oxide, this oxide will react with this, this will generate, a oxygen deficient surface. And that oxygen deficient surface selectively absorbs the CO2 at the surface before the hydrogenation process. Sometimes it can enhance the conversion if you have a small amount of moisture in the system, but it should not be very high, then it will decompose the sample also. So there is an optimum level, whatever the mentioned in a tolerant level, if you can keep it in your system, sometimes it can be helpful in the CO2 conversion. I'm talking about when you connect the CO2 capture and conversion, this point may be helpful. Depends on the material.
In direct air capture, they use moisture. So there is no problem. They use water as a solvent for the direct air capture. So this is not an issue at all. But when you go to a large single point source, the level is pretty low. So it should not be a big problem.
And also they generate at higher temperature. Most of them might have already separated. Yes.
any other questions? Yeah, please go ahead.
The next question is for audience, and it is for Dr. Alu, ma'am. Ma'am, what are the methods available for monitoring of greenhouse and greenhouse methane?
I'm sorry, Anshika, I'm not able to get the question. What are the methods?
For the monitoring for the monitoring. What are? Am I audible, ma'am?
No.
Yeah. Now you are audible. Please, Anshika,
please
go ahead.
repeat the question. Yeah, you are.
What are the methods available for the monitoring of greenhouse gases such as carbon dioxide and methane?
Usually, see, when it comes to lab level, of course, DC is being put into use, but when it comes to field monitoring, it is more of NDIR based, okay, analyzers which are readily available in the market. Like we are talking about, when it comes to flue gas emissions, there are very sophisticated multi-gas analyzers which are available. The brand also, I can tell you, it's a Testo brand, which is working very effectively to monitor CO2 in the presence of SO2 and NO2 as well. So these are the multi-gas analyzers which are readily available in the market for monitoring CO2.
Ma'am, I have one question.
Yeah.
Is it possible to develop solar trees to capture CO2 and utilize as raw materials for industrial use?
Yes, it's a very good question. I mentioned that one of the approach which is being pursued at our institute is to use panel and put it for carbon capture, wherein essentially what we are doing is we are retrofitting a reactor with the panel for harvesting the heat, which can be put into use for regeneration. And in the night, the same solvent can be put it into carbon capture. And I truly appreciate the thinking which has prompted you to come up with a solar tree which could be fixed up with the panel so that it appears like an artificial tree taking up the CO2. I was majorly talking about a leaf made of panel having these systems of CO2 absorption and regeneration, but obviously the leaves can be developed into a tree.
Thank you, ma'am.
So does that answer my question, Madhu?
Yes, ma'am.
Yeah.
Are there any other questions, Madhu? And Anshika and Sunita, please. Are you received from the
Nope.
auditorium? Any questions?
Yeah, I cannot find any right now.
My question is to Sukumar Devate, sir. How do we address the spent solvents after the capture of CO2 from flue gases?
Why? If you go to the flow sheet of solvent capture, regeneration is part of that. It's not an issue at all. Only problem is when the people use MEA, you lose a lot of MEA by various destruction, including degradation. So you have to have a loop for recovery of MEA and makeup solvent. But in a mixed solvent, this loss of degradation has been reduced, and therefore the makeup solvent gets very low in terms of saving the cost.
Sir, how do we address the VOCs from the solvent regeneration process?
See, these are all making the CIS plant tight and recovery as best as possible. These are all design issues. They are not technological issues, and these are being practiced. If you are a chemical engineer, you can design a system appropriately. It's not an issue at all.
Thank you, sir.
It is an issue when you use MEA because you lose a lot of MEA by degradation, and therefore it's a cost factor and it is a loss factor, and you have to do make up MEA. But when you use mixed solvent with promoters, the loss is low, much reduced, and therefore it is not an issue. Okay.
I think I can see a question from Karthik. So can you get it? There are few questions from the audience.
Seems to be an active audience. Good.
Because we are having 112 audience right now, sir.
Yes,
The
yes.
auditorium. So I can see in the chart. Yeah. So there is a question to Dr. Devata Saab. As you mentioned regarding the algae for the carbon sequestration, could you point to which particular species of algae which could be used for carbon utilization? It is asked by somebody.
I'm not too sure I can answer that question, but there are people who have demonstrated algal process in two ways. One is just in a raceway pond, Another is a group which is using wastewater as well as the algal pond to generate water, treated water and biomass. And biomass, what was produced in NTPC was just a biochar kind of thing. But I've seen people trying to moving towards high lipid content, but that is still not yet fully achieved. But you can generate biochar, and people are buying for many applications. There is one near Chennai using sugar distillery. They are using sugar distillery wastewater, and it's a combination of distillery and sugar. So they're using wastewater because it's a high nutrient wastewater, and they are capturing CO2 and produce biomass. Yeah.
Can I add something, sir?
Yeah, please. It's a large scale plant.
Okay, yeah. Spirulina is being used extensively because, because that offers a lot of nutrients and other possibilities. Spirulina is one species, and I think
Spirulina is the one which is used in distilleries also.
right. Chlamydomonas, these are some of the species which are being put into use for algal sequestration.
There is a question from Hariram Kumar Samudrala. So it is question to Professor Sebastian Peter. Is it possible to convert CO2 to glucose in near future?
That is my dream. I used to tell my students, okay, so target to glucose in future. So we step by step we cross C1, C2, now we are C3, and so the nature is so beautiful, then efficiently converting CO2 to glucose. And if we can mimic that in lab, that to able to manage the production. One example, when I was in one of award function, in a final round, the committee asked, can you convert CO2 to glucose under Mars surface, say for example. So that's a dream, but it's very difficult. I can tell you they're very difficult. So because you have to make a C bond C, bond C, bond C, bond 6C, you have to make a CC coupling. That's some massive, challenges, and it may take some time, but again, the efficiency we have to think about.
See, these things are when we need to target chemicals which are large, large consuming products, and then it should be as easy as possible. Not to look at let's look at C3 level, C1, C2, C3 level, methanol, methane, alcohol,
Ethanol,
ethanol, and then go to alkynes, then get into ethylene oxide and ethylene glycol. You start using chemicals towards replacing bulk chemicals. That's what we should target. Otherwise, as I told you, CCV has a limited scope. So you have to do a lot of innovation to substitute bulk chemicals so that the consumption of CO2 can be increased. As it is, CO2 demand is low because they are used only for urea, and things like that, or soda ash and things like that. And they are produced synthetically. Whereas when you're doing it this way, you need to look at economics and look at large consumption.
But there is
Sir,
a question
here-
to Dr.
This is to
Yes, Sunita, please.
Dr. Sebastian. He said that CO2 to C1, C2, C3, we have generation of CO which is inevitable. So how do we address that?
Not inevitable. That we have, say for example, we produced acetic acid, say for example. In that acetic acid production, we got the formic acid, say for example, 20% and 80% acetic acid, we got it when one such work, got it. So there is a way to tackle the CO is, I mean, there are two pathways you can go to C1, C2, C3. So it can go either through CO or the format pathway. And if the catalyst is actually not able to release, I mean, or dissociate that CO at the surface efficiently, or if it is inefficiently released that one, during the process, some amount of CO will come. So what we do actually, we tune the surface in a Sabatier principle, the fundamental concept of chemistry. I mean, so Sabatier principle, how optimum way of, CO be present at the surface and hydrogenate and then reduce the amount of CO. That's the trick, the chemist or catalysis community doing. So we can do it, but at a, if you don't understand that, I mean, the mechanism in depth, I mean, it may be difficult. We cannot eliminate that.
Okay, thank you.
Sir, there is a question from Mr. Karthik, M. Karthik, to Devata sir. The question is, besides CCU projects and decarbonization of Indian industry, agriculture, waste and power sector, how much approximately it is going to cost India to achieve net zero target by 2070?
I don't think anybody knows that answer. Yeah, see, the India is committed only for 2070, while most of the countries are committed to 2050. It's only commitment. It's a promise which pledge people have made. Because Paris commitment was there, but nothing happened. Now, post Paris, now people have made commitment, but India deferred it by 2 decades. And one of the reasons why CCS storage is deferred in Indian policy is that it's not economical. Today, most of the storage is driven by policies funded by government. You take US, you take Norway, huge funds are going into storage facilities. It's not economical otherwise. So they fund it and they drive the policy. But that is not what India is looking at. India is looking at how do you manage it. So it's buying time. They have bought 20 years extra time to understand how do you make it economical. Maybe internationally developments will take place. Global finance, there is no global finance today. Unfortunately, I get involved in politics of carbon. So there is no global finance today. There are talks on it, but there is no global finance. So it's not easy to say how much it's going to cost. We are only looking at other options, including renewable. But I can tell you, impossible to substitute everything for renewable. So you have to do a mosaic of options, and CCV will be one of the options, one of the mosaics in our frame. Yeah.
The last question is, I think I could not, only one question I can see on the screen. That is, this is Ankush Dilip Kullarkar. So to Dr. Sadhana Raylu madam, which is feasible process, carbon dioxide hydrogenation or carbon dioxide splitting?
According to me, the most advanced process is CO2 hydrogenation as of now. And to some extent, there are definitely reports existing wherein CO2 has been split into oxygen as well as CO. And I think it is in demonstration scale, but there are a lot of issues associated with it. That is thermochemical approach, basically. So designing of thermochemical reactors and furnaces are major challenges associated with it. And second, of course, is a lot of enzymatic work is also going on splitting CO2 to CO and oxygen, which is at very, very developmental stage. So as compared to the three approaches, I believe that CO2 hydrogenation using the hydrogen, which is coming from water splitting to make products like methanol, etc., is in relatively advanced stage.
Thank you, madam. And the last, I have one question to all the members, panelists. So this we can treat as a panel discussion question because we are having a very short time. So the question is, what is your recommendations to way move forward net zero 2070? Sir, Devata sir, please.
No, yeah, as I said, I have already answered the question. There is no single solution. Renewables and energy efficiency. We are working on DST. I'm involved in DST mentorship on energy efficient, net zero, buildings, net zero refrigeration. We are working on it, because you have consumption is going in different direction. Industrial is one, building is very major consumption. So we are looking at net zero buildings. It's not just increase the insulation or anything like that. How to minimize consumption of buildings in terms of cooling, building, efficiency, materials. So there are many options and many attempts towards that. There is no single solution. Thank you.
Professor Sebastian.
Yeah, so it's, I mean, as I also mentioned in my introductory slides, I mean, it's I mean, there are a lot, it's massive, effort. I mean, it's very difficult to, achieve that one. I just give an example. I mean, I don't know whether I mentioned this in your platform. See, we are all equally responsible for the emission. We all accept. So somebody say that, okay, I'm not responsible because I'm not using any automobile. No, you are, say for example, I text a hi to my friend in WhatsApp. Hi, hello. So that is equivalent to maybe one molecule of CO2. So how it is related actually, you are using morning to evening and you are going to charge your mobile, say for example. And the electricity that you are using for charging, that is coming from somewhere power generation sector. Okay. And it's not just urbanization, it's also technology development, IT development. And we are moving in such a massive exponential growth, I mean, especially country like in India. And we are actually depositing large amount of CO2 also at the atmosphere or earth crust, etc. So net zero, I mean, in the same phase, if you don't move it in the same way, whatever released, I mean, CO2, sequestration or CO2 capture, these are all well matured technology, but there is a limit also, there's a saturation limit also, geographical limit also, unfortunately. This is also mentioned, I mean, so we have our own problem of storage, our own problem of sequestration. That's what, I mean, me and all came, so how to utilize them. And utilization is in the form of, I mean, maybe methanol. Then again, the question is actually methanol, again, you use it for energy and then again CO2 will produce. Still, it is not, CO2 still there. So we can create a sustainable cycle of utilization and reuse and if we can reach that in that loop. So you are like in a revolving, I mean, if we can reach that loop, then we can do that one. There is a beautiful article by IPCC. There are different strategic plan and they're listed out plan A, plan B, plan B, and how we can, the aggressive way. And they compare that, plan with the plans of the European Union, say for example. And by end of 2090 or 2100, if you are going with a very slow plan way, it is around 300 gigaton of CO2 in the atmosphere of India. If it is a plan G, it will be around 60. I mean, that's a different plan by 2040. So that is equivalent to US, but the other side equivalent to China. So this is, combination of policymakers, combination of academic industries and industry sectors. And if you are working together, probably we may achieve the net zero. It's not one single person. So from the basic of a human, what you call society, we have to understand that what is impact, who is responsible. And then if the government can come forward with this policy plan and all, we can do. But it's really challenging task, really challenging.
Madam,
Hello,
your
everyone.
opinion?
Yeah, actually, I think there are three pillars essentially. One is the energy sector, wherein we have to focus on improved energy efficiency, decarbonizing, so on and so forth. Second, of course, is mobility. That is also contributing huge towards the greenhouse gases. Third, of course, is industry manufacturing units where there is no control. Different industries like steel plants, so on and so forth. And green buildings and infrastructure, as sir has already mentioned. Fifth is agriculture. So these are the 5 pillars on which we should be focusing on if we have to go in for net zero, meeting the target of net zero emissions by 2070. So now the major focus is more on energy sector, that is decarbonizing, improved energy efficiency. To some extent, efforts have been initiated in the mobility sector also. But yes, focused efforts are also needed in the agriculture sector. In fact, there are a lot of committees now constituted by DST, wherein agricultural residues, etc., are being converted by taking into consideration the GHG emissions which are associated with it, like it's being converted into biogas to make it CO2 neutral, so on and so forth, and industry, of course. So I believe these are the 5 pillars which will contribute very strongly towards net zero emission, not forgetting very important green hydrogen.
So I want to cite here 2 important issues discussed by Sri Nishit Radia. So one is he expressed about the boiler emissions, which contain 18 to 20% of carbon dioxide, which can be utilized in the process. The process requires 40% of the carbon dioxide during the soda ash processing. So this is one thought he has shared during his presentation. The second one is carbon dioxide is converted into sodium carbonate by concentrating to 90%. So these 2 important issues definitely give an idea about in real industrial applications, how we can manage and how we can convert carbon dioxide into usable products, or we can make them into a process. So these are 2 important aspects he expressed during his talk. Unfortunately, we delinked because of his travel. So I think these are the 2 important issues he raised during his presentation. So with this small discussion, yes, Anshika, please.
I have a question in the line of our ambitious goal of becoming carbon neutral to 2070, but we still don't have any legislation and no extended responsibility on the producers. It is more of a political issue, but don't you think that we should be facing towards it?
Sir, Devata sir, please.
Yeah. See, as I said, it is a global political situation, not just for India. It's a global political situation. And India is a country which is growing. And therefore, India is saying that we need carbon space. There is a world definition for carbon space. How much the space can still take CO2. And that space is still occupied by most of the developing countries. They are continuing to emit more CO2 without bothering about other developing countries like India to develop. So India is negotiating for 2 things, for carbon space and technology transfer with funds. So it is a political, so we cannot be discussing this. And that is one of the reasons why carbon sequestration is not discussed much more openly than carbon valorization.
So thank you very much, sir. And we have a much more discussion and questions from the audience rather than the presentation. So it itself indicates that we are discussed a lot, and all the discussion is recorded by MST. So this will go as a file, and whenever there is a meetings, they will display this, and they can take. It will be an useful material in the archive of the MST. So now come to the last point, that is a vote of thanks. So that is I'm very thankful to our director, CSR Nidhi, Dr. Atul Narayan Vaidya, who is instrumental in planning and execution of the project. This iCEN-52 event, and Dr. Sadhana Raidu, who is the event coordinator, and because of lot of meetings, online meetings and others, so she given me the assignment to me so that I am able to do this, organizing this. I'm thankful to you, madam, for your technical program which was designed by you. And I'm thankful to iCEN organizers. This is organized by under the leadership of Dr. Gopal Iyengar, who is the team nodal, and Dr. Mahendrapi Darorkar, CSIR nodal, and the Palak and his team, who are instrumental in providing the connections and virtual auditorium. Thankful to you for nicely conducting this e-communication. I'm thankful to you. And very much thankful to Dr. Sukumar Devata Saab. He is always with us throughout his program and all projects which were handled by the NIRI. And sir, we always require your mentorship, your guidance in your ongoing programs. It is a pleasure to see you again and again, and it is a pleasure for us. So I am thankful to Sri Nishit Radia, who is the CEO and president of GSCL. He is a very busy person. Still, he is able to speak with us for a few minutes. I am very thankful to Radia Saab. Even though he is traveling, he is able to link with us. I am thankful to you, Sri Radia ji. And I am thankful to Professor Sebastian Peter. So given a very wonderful academic perspective of the carbon dioxide capture, especially by using the inorganic solid systems, which can be work as an effective carbon dioxide capture materials, not only capture, but converting into a different useful products. So I really impressed your dream of converting CO2 into glucose. So hopefully we will listen to you very soon in NIRI. And I'm thankful to Dr. Sadhana Railu, madam. She has given an overall perspective of the NIRI's research work at the materials perspective, what type of different types of materials used for the carbon dioxide capture and valorization, and her thoughts, especially integrating the photonics and biomimetic system for effective capture of CO2 is a very impressive, and we are also following madam to develop few more high-class materials which can be useful at an industrial scale. Thank you very much, madam, for your nice and informative talk. Thank you very much. So now I must say thanks to the all audience who are there from the 10 a.m. onwards, and they are actively participated in this event. I'm thankful to all the audience on behalf of the iCEN-52 program. And at the last, not the least, my team, which include Dr. Sinta Shastri, Miss Madhu Sharma, Miss Anishka Yadav, Miss Neha, they all are ACSR PhD students, and Mr. Vivek. So I'm thankful to all these people who are there for smooth execution of this project, this event. So thank you one and all, and we hope that we meet some other platform to discuss on these issues, and we are very much looking towards to work with you and your research areas. So with this and the permission of all the speakers and the director and Dr. Sadhana Railu, I am concluding the session here by saying thank you to all.
Okay. All the best.
Thank you, sir. Thank you.
Bye-bye.
Thank you.